Good morning, Physics 131, welcome. I can see 365 of you here right now. It's another nice day in Toronto, nice day for bike ride. A little brisk, but I, wore a jacket and it's all fine, not raining like yesterday. Let's go on to the screen share. As usual. Share. Okay, so the plan for today, we're going to finish up chapter 5 on circular motion. Get my pen set up here. And we are going to take 10 minutes in the middle to do one of these team up group quizzes, in which you're going to have to go onto Microsoft Teams and have 3 windows open, because you've got this Zoom, you got Microsoft Teams, and then the Quarkus team up quiz, which should show up in a couple minutes on the Quarkus under module 3. So you should be able to find it there. Actually, and before we get going, this is Crazy Friday. So let's do a poll in which we choose democratically what is the crazy filter of the day. Feel free to click in there. Basketball, tennis ball. Let's put those over here. Okay, what's the verdict here? Oh my God. Well, it's any more votes? It's not quite a landslide. Let's take a look. Oops, share results. Yeah, so it looks like we can do it. All right, so let's try to do that. Second place, by the way, was going to be beret. So you guys like these little things rather than the facial hair. I'm going to have to keep that in mind. So if I go to video, choose video filter. Somewhere down here, there it is. Okay, good. So how does that look? Great. Awesome. Okay, this is the other thing. The Physics 131 Help Center is moving off of Gathertown. We find that the audio quality, the whiteboard, shareable whiteboard, all this stuff seems to be better on Zoom. So that's where the Help Center is going to be. There's the passcode for it. That's actually where I'm going to go after class today from 12 to 12:30. I'm going to go over on that other computer. I'm actually on it right now. On the Help Center and take questions over there. And then when the TA comes, I'll make that TA a host and I'll kind of pass the baton that way, sort of unify some of these things a little better. So it's good to know where the Help Center is. All right. And then actually, let me see if we got anything going on in the chat. Participants list. Okay. I'm glad you guys are liking the look. Put this up here. Okay. Oops. All right. Crazy Friday. More. Looks like you guys are set. So what I want to do is actually do the example that I was hoping to do last time. This is the banked curve example. So you have a highway which has a curve in it, which if you saw it from above would be a portion of a circle with a radius of 70 meters. And it's banked at a 15-degree angle. So I'm not going to do the whole sketch. I'm just going to show you the one that was given to you as part of my sketch and translate. The top view is showing that this portion of the curve has R equals the 70 meters. R equals 70.0 meters. And then there's the angle, theta is equal to 15 degrees. The thing is banked like a kind of a race car thing or something. So you can only really see the banking angle if you're viewing it from the rear view. And then the top view is the only way you can actually see the circular path. So we are going to go at a constant speed, it says there, v sub 0, but on a curved path. So circular path means that there is an acceleration. A sub r is equal to v0 squared divided by r. Okay. So if you are staying on a circular path, you must have a component of the acceleration towards the center of the circle, which is v squared over r. Otherwise, you won't stay on that curved path. You'll just go on a straight line. Like if you're going constant velocity, you go on a constant speed at a straight line. If you're on a curved path, you must have an acceleration which is going towards the center. So it says there without friction, which is kind of interesting. So F sub s equals 0, so that's possible. You can, static friction is a self-adjusting force. Okay, and I'm going to define system is the car. R is going to be the road. So when I simplify diagram, I'm going to actually draw, you can only draw the force diagram from the rear view. And then in that case, you got the force of the earth, gravity of the earth on the car, okay, which is your mg. And then from this angle, you've got a normal force perpendicular to the road surface of the road on the car. So we're going to assume that the only forces on this car are normal and gravity, because there's no friction. So I have to find the angles here. So if this is the rear view, and here's your theta, and here's your normal force, then if you were to draw a dashed horizontal line there, that would be your theta. And if you were to draw a dashed vertical line there, this would be a 90 degrees between those two dashed lines. So this angle right here is theta. So this angle that I kind of care about right there is 90, sorry, that's wrong. Slow down. If it's 90 degrees between these dashed lines, and this is theta, then this is 90 minus theta, right? And then this one, since it's perpendicular to the slope, that's 90 minus theta. So that's equal to theta. So when I decompose the normal force, if this is normal, then this angle right here is theta. This is, so the other thing I have to do is that the acceleration is towards the center of the circle, a sub r. So I need to define plus r to be towards the center of the circle. So that's a very key point. Usually in previous problems, we've been able to kind of define the x and the y sort of whichever way we want or different ways. In these kinds of banked curve questions or any circular motion question, you always want to define the plus r direction to be towards the center of the circular path that you're on, so that a sub r can be v squared over r, the radial acceleration. So now you've got the normal force has a component in the r direction, and I guess we can put y to be up. So then the normal force has a component in the y direction as well. So once again, I think n sub r is equal to n times sine of theta, and n sub y is going to be n times cos theta, as defined here. So these are all the tricky parts. And then I'm going to also say that a sub y equals 0. The car doesn't accelerate up or down. How are you guys doing out there? Fia, I noticed that you had your hand up. Do you have a question about this stuff?
Yes. Can I ask, if there is friction, which direction would it point to?
That's a great question. So if there was static friction, which way would it point in? So I'll give you the answer. The answer is that it actually depends. We're going to find the exact speed that the car can go around this curve without friction. If you speed up and go faster than that, then the static friction that's needed to keep you on the road is down the hill, because you need more to have a larger acceleration. If you go slower than that, like if you stop, for example, then the static friction will be up the hill, because You need it in order to not slide down. It's whatever direction will prevent you from slipping on the road. So static friction is one of these really weird self-adjusting forces that it sort of chooses its own direction based on whatever is needed in order to prevent that object from slipping on the surface. So great question. But in this case, there's no friction, so we need everything just from these two forces. So we're going to go to do our equations next. Let's just go to the next one. So I'm going to do one of these tables, the R components and the Y components. And there's only two forces, the normal force and the F sub G, right? So the normal force is going to be, we said the R component is n sine theta in the plus direction. This is towards the center of the circle. And the Y component is up and it's n cos theta. And there's no R component of the force of gravity, and the Y component is negative mass of the car times G. System was the car. And then since A sub Y equals 0, that means that the sum of the forces in the Y direction is equal to 0. That's equal to n cos theta minus mg. So that what that means is that, and this is weird, the normal force is the mass of the car times G divided by cos theta. I don't know if you ever saw that one coming before, but in a banked curve problem like this, the normal force is mg over cos theta. Just kind of different. So, okay, so now we've got the normal force. Then the next thing is that you say A sub R, which is equal, there's two equations from Newton's second law. It's the sum of all the forces in the R direction divided by the mass of the car. So that's just going to be n sine theta divided by the mass of the car. So I can take this now n and go and plug it in to over here since we've solved for it. So this equals mass of the car times g times sine theta divided by m mass of the car times cos theta. And at this point, the two MC's cancel. Doesn't depend on the mass of the car. Interesting. So A sub R is equal to G sine theta divided by cos theta, okay? And that also is equal, we know, to V sub 0 squared over R. We know R, we know theta, we know G, so all we have to do is solve for V sub 0. So I get that V0 squared is equal to G times R times sine theta over cos theta. I'm going to choose the positive root because you can't have a negative speed. So V0 is equal to the square root of G times R times sine theta divided by cos theta, which is the square root of 9.8 times 70 times sine of 15 divided by cos of 15. I plugged all that into my calculator, and I got V0 is equal to 13.56 meters per second. It looks like there's two significant figures in the angle there, so let's just round it to V0 equals 14 meters per second. And this is about 50 kilometers per hour. Okay, typical road speed. So what's interesting is that if you go around a banked curve that's banked at 15 degrees and it has a radius of 70 meters, if you go exactly at this 50 kilometers per hour, then you do not need any friction to keep you on that curve. It could be a perfectly icy road, and as long as you keep it at exactly 50 kilometers per hour, you can just cruise around the road entirely being kept on the curve by the banking. If you slow down, you're going to slide down the hill. If you speed up, you're going to go off the hill and end up in the ditch on that side. But if you go just at that exact same speed, 14 meters per second, you'll stay on the road. Yeah, wouldn't your back spin? I guess we're assuming that the car is a point object, so it's not actually rotating or something like that. Oh, Annie pointed out that sine theta divided by cos theta is tan theta, so that's true. That would save me a step. And then Sunny Woo's got a question, is radial force not a force? That's an excellent question. So notice I didn't draw the radial force on my force diagram. So the force diagram only keeps on forces that are external forces of some other object on that object. And radial force is not that kind of a thing. Radial force in this kind of question, it's the net force. Okay, so this actually, if we go up here, this right here, the sum of F R, that's the radial force. It's a bit tricky. And you don't draw the net force on a force diagram. It has to be the forces on the force diagram, the real forces have to sum up to be the net force, or in this case, the radial force. So great questions. Yeah, pretty good here. So let me just break for time. Osaze, did you have a question?
Hello?
Hi.
Hi, yes. Someone had asked a question earlier about friction in this case. Well,
Yes.
assuming there actually was friction in the question. And
Yeah.
so you had answered mentioning friction with regards to sliding down the curve, well, the angle, or going up. And so one thing that I was confused about is would there also be friction in the direction of the car moving itself at that particular point?
Yeah. This is sort of 3D, isn't it? Right. So that's a great question. If you go back here, so what I was saying before is that it is possible to have kind of a static friction. Static friction has to be perpendicular to the normal force, right? So you could have static friction going down the hill or up the hill, perpendicular to normal. But there's another direction, isn't there? Which is like into the page and out of the page. So that could happen. That could happen if you were speeding up or slowing down as you were going around the curve. Does that make sense? So if you were, applying the engine force so that you were accelerating, and by that I mean not radial acceleration, but if you had, it's called tangential acceleration. If you're going on this path and speeding up, then there would be a static friction force going into the page on this diagram, which would be speeding you up.
Okay, so that tangential acceleration, that would essentially be like the acceleration for the opposite force if you were to speed up in the direction of going into the paper?
Kind of. The net force of the road on the car, the static friction of the road on the car is actually in the same direction as your acceleration. So if you're speeding up, it would be into the paper. If you had the brakes on, then it would be up out of the paper, I guess, if this is the rear view, right?
Okay, thank you, Professor.
Yeah, you're welcome. I always love to get a bit of discussion going here. Okay, excellent. So next thing is, that was the stuff actually I missed from last time. Today's topic to finish up chapter 5 is about the universal force of gravity. So let me just see. Yeah, there we are. So Isaac Newton recognized long ago that gravity is an attractive long-range force between any two objects, and that's detailed out there. But basically, if we have two masses, and that's why I grabbed the basketball and the tennis ball, M1 and M2, and their centers are separated by some distance r, then both of these objects attract the other with a force given by Newton's law of gravity. And there's a constant here. The constant capital G in SI units is 6.67 times 10 to the minus 11. So this is the idea of gravity. Any two objects with mass will attract one another. And this is not the electric force, it's not magnetic, it's a whole other force called gravitational force. It's always attractive between any two masses, and it's always pulls them directly towards one another. So these two forces are equal and opposite. According to Newton's third law, they must be. And they also have the same magnitude, which is G times M1 times M2 divided by the distance between them squared. So if M1 is 1 kilogram, and if M2 is 1 kilogram, 1 times 1, and they're 1 meter apart, so divided by 1 squared, then the force would be 6.67 times 10 to the minus 11 newtons, pulling these two things together. So that's really, really small. And that is the reason why we don't normally observe the gravitational force in our everyday lives. But yeah, if you're even just at a romantic dinner and you're sitting across the table from another human being, 1 meter, there's going to be an attractive force that's pulling you towards the other person, the gravitational force. So it's a good thing to bring up. I've measured it. So there's actually if you look at all the in-person courses at U of T, there's not many, but the lab courses in physics are in person. And so Physics 224, Practical Physics 1 is an in-person course. This is just upstairs. I took this photo. It's of the Cavendish experiment. So what you have is 2 lead balls, and they are on a little cantilever, and they're suspended by a torsion wire, which goes up here. And so, or actually there's 2 lead balls that are behind the glass there so that there's no wind. And then you put 2 bigger lead balls outside, and you measure the attractive force between the big lead ball and the internal lead ball by seeing where they settle. And so this torsion wire gets stretched just a little bit. You reflect a mirror, a laser light off a mirror in the middle, and you have to find the dot on the wall. It's a very, very small force, but it's measurable. So it's about 10 nanonewtons is what you measure. You can do it in about 2 weeks, so that's a fun course to take. Let's do an example. Object 1 with a mass M1 sits at the surface of a giant spherical rock which is floating in space. So there are just 2 things floating around in space together. I see where they are. My notes are a bit confused here. There it is. So we've got just a blue here. An attractive force. So this distance right here, R, is the radius of the circle. And since M1 is very small compared to M2, M2 has a radius of 6,400 kilometers, equals 6,400 kilometers times 10 to the 3 meters. Okay. Distance between centers. So that's important to notice. If you have 2 spherical objects, you're measuring the distance between centers as will give you this force. So we assume that these are isolated objects way out in space. No other objects. We'll define the system here equals M1. And so we are trying to find the force of gravity, F sub G, of 2 on 1. Right? And so you're just going to use that F sub G of 2 on 1 is equal to G times M1 times M2 divided by R squared. So it's FG is equal to 6.67 times 10 to the minus 11 times M1, we don't actually know, times M2, which was 6 times 10 to the 24 kilograms, it's a big object, divided by 6,400 times 10 to the 3 meters squared. So I'm keeping everything in SI units because this 6.67 times 10 to the minus 11 has some SI units. I'm not going to write down the units because they bother me. It takes so much time. But I typed those onto my calculator and guess what I got? 9.8 M1. And if I did check my units carefully, the units turn out to be newtons per kilogram, or which is the same as meters per second squared. So does anyone have an idea? They want to type into the chat window of what would be a good name for object 2? Okay, seeing a lot of people typing Earth. So let's choose Earth. Good job. That's the whole idea, right? Is that if you happen to live on the surface of a large planet with radius r and mass m, you can write the gravitational force simply as F equals mg, where the quantity lowercase g equals uppercase G times the mass of your planet divided by the radius of your planet squared. And here on this surface of this planet, that's about 9.83 if you're at sea level, 9.71 if you're at way up top of Mount Everest, about 9.8. Okay, so we're gonna do this team up quiz. This was a news article. So Kate Rubins, pictured here, launched on her second mission to the International Space Station just on Wednesday. She's currently up there in orbit. These are the two other astronauts she's working with. She's going to be up there for about 6 months, returning April 2021. She's a Bachelor of Science in Molecular Biology, PhD in Cancer Biology, and here she is pictured doing the first DNA sequencing in space. So what I want to do right now, you should be able to go onto Quarkus right now and see this thing, Module 3, Chapters 5 and 6, the Team Up Quiz, Module 3, Chapter 5. This is a group quiz to be done in your pod team on Microsoft Teams. So I'm going to mute on this for 10 minutes, and what you should do is in a separate window, open up Microsoft Teams, and one of you in the pod should place a video call to the other members of your pod, in your pod chat. And then when you're in your pod chatting, first decide who's going to be the driver. All of you, all 3 or 4 of you should log into Quarkus. If you're not the driver, just wait. If you are the driver, click on the Team Up Quiz, click Go to Tool, and click Create a Group. Then go back to the Teams window and let everyone know what the session ID is. And then wait for them, because you don't want to drive off alone. Non-drivers, once you get that session ID, you go to Quarkus, find the Module 3, click on Go to Tool, and then instead of clicking Create a Group, click Join Session. And then type in that ID that the driver gave you. And then you'll all be working together. Once everyone in the room is in Team Up, you'll see each other in the Team Up window, and you can start going through the questions. There are 3 questions. Please achieve consensus before your driver submits. You can begin now. It's 11:37. If your pod mates are not here in Microsoft Teams for whatever reason, you could go to the TA Help Center just over there. And I could throw you into a breakout room, but it's only got about 21 breakout rooms, so there's limited space. But at least you could work with some friends on it. So I'm going to go over there right now. The other thing I'm going to do is pause the recording for a bit. So hopefully you were able to submit your Team Up quiz at the end. Once you've answered all the questions, you hit the driver has to submit the quiz, which should save all your scores. I want to talk right now about the answers. So the first question was, astronaut Kate Rubins is currently living on the International Space Station, which orbits at 370 kilometers above the surface of the Earth, which is a low Earth orbit. Assuming Kate has not changed her mass since moving to space, what is the force of gravity of the Earth on Kate? And I'm thinking compared to what it was when she was down here on Earth. Is it 0? Is it the same as the force of gravity on her while she was on Earth? Or is it a little bit less? So the answer I was looking for there is actually it's a little bit less. And I'm gonna talk about that in a minute. But, okay. One question is, right now you are on the surface of the Earth and Kate Rubins is 370 kilometers up. What is the ratio of the distance from you to the center of or her to the center of the Earth to you to the center of the Earth? So that's not hard to actually calculate. All you do is you would say the radius of the Earth, you can look it up, or we talked about that, of the Earth is 6,400 kilometers. Kate's distance from the center of Earth is going to be 6,400 plus 370. So it's going to be 6770 kilometers. So that's kind of interesting, right? Is that if you take the ratio 6770 divided by 6400, you get that it's 1.06. She's only 6% farther away from the center of the Earth than you are. Okay, and so that's why the gravity is only 8.9 meters per second squared, this acceleration constant due to gravity at low Earth orbit. So I'm here telling you right now that the International Space Station is accelerating down towards the center of the Earth at 8.9 meters per second squared. So this was the question is, why doesn't it just crash into the Earth? Is it A, it's not actually accelerating at 8.9 meters per second squared towards the Earth? B, because as it accelerates towards the Earth, it's going sideways, and this is the circular path argument, actually. That's what I was looking for. Maybe it should have, maybe the wording wasn't great. Maybe it should have said something about a circular path. It's accelerating because it's on a circular path. C, this acceleration is compensated by rocket blasters, which continuously point away from the Earth. That's not true. When you're in a low Earth orbit, there's no rocket blasters needed. And D, 8.9 meters per second squared is not noticeable acceleration. It would take millions of years to travel 370 kilometers in a straight line at that acceleration. That's definitely not true. If you stop moving sideways, you would plummet to the Earth really quickly. It would take minutes before you would hit the surface. Okay, so orbit is drawn to scale. As you're going around, Kate feels weightless because she is in free fall. So weight that you feel is actually the normal force. If you take away the normal force, you don't feel the weight. You really can't feel the gravity itself pulling down at you. What you feel is someone else pushing on you in the, like the surface of the floor pushing up on you. Okay. So let's think about this a little. I'll do another kind of example. Here's the curvature of the Earth. So you don't often notice it because the Earth seems flat, but my idea is that if you were to go sideways 8,000 meters, then it turns out that the radius of the Earth is such that it curves downwards 5 meters for every 8,000 meters you go sideways. So if you launch a ball horizontally, say consider a ball launched horizontally so that the initial y component of the velocity is 0, so sort of like this. Okay. How far does it fall in 1 second? Well, so this is V0x, so V0y is 0. So that means that the y is going to be 1/2 times a sub y times t squared. A sub y is negative g, so it's going to be 1/2 times negative 9.8 times 1 second squared. You're going to get negative 4.9 meters. So about 5 meters down. So what this means is that, I'll try to write it here, if you go 8,000 meters per second, the curvature of the Earth makes the surface stay the same distance away. Can you imagine that? So you're dropping down 5 meters, but the surface has dropped down 5 meters. So you're now no closer to the surface than you were 8,000 meters ago. And if you continue at that same speed, the surface will keep dropping and you will keep dropping and the surface you'll stay the same distance above the surface. That is what is called an orbit. Okay, so flat Earth approximation is that the force of gravity pulls you straight down. Okay, that's sort of what we've been assuming. You define this is your x, this is your y, and all that stuff. You know, a sub x is equal to 0, a sub y is negative g, all that stuff. That's called the flat Earth approximation. In real life, the Earth is a sphere, so the force of gravity is not in a constant direction. The force of gravity pulls things towards the center of this big massive rock called the Earth. And that is why if the sun is up here, okay, and it's right now almost noon in Toronto, if you're in Bangladesh over here, it's, you know, the middle of the night or something, right? So you can prove that just by the existence of time zones, you know that the Earth's not flat. What time is it here? Yeah, I've got 5 minutes. So I think I've got time to do a quick little example. How fast would you have to drive in order to be weightless, i.e. no normal force needed to support your car? So here is the Earth, here is your car, okay? And the circular path is going around the Earth, the surface of the Earth. Okay, so the radius is 6,400 times 10 to the 3 meters, 6,400 kilometers. That's your R. And you've got some force of gravity. So this is your A sub R will be downwards. So we're going to say, assume that the normal force of the surface on the car equals 0 for some reason. So what you'd have is A sub R is V squared over R. And there's your force diagram, is the force of gravity of the Earth on the car. Okay. So the sum of forces in the R direction is equal just to mass of the car times G. We're going to define plus R is down. Okay, so the represent mathematically is that the A sub R, which is equal to V squared over R, that's the net force, is equal to the sum of all the R forces divided by the mass of the car. So it's going to be mass of the car times G, that's the sum of all the forces, divided by the mass of the car. Once again, the masses magically cancel out. And so you just get that V squared over R equals G. And you're trying to solve for how fast, so I should put up here, we're going to find V, right? So V squared equals GR. Choose the positive solution. So V is equal to the square root of GR. So V is equal to the square root of 9.8 times 6,400 times 10 to the 3 to convert it to SI units. And that's where I got 7,900, it's about 7,900 meters per second. So that's very fast. And again, it's like around 8,000 kilometers per second. So that's very fast. And you can't drive that fast, you would burn up. If you could drive that fast, your car would instantly get vaporized by the air resistance, and you'd just be plasma. You'd be killed. Okay. Let me just see. So Arman asked, when will we see our midterm 2 grades? That's a great question. So the markers are working on it. They have the weekend I've given them. Again, they're each doing about 30 hours because they're each doing one problem. And also they have to do the alternate sitting. So I've given them till Monday at 9 a.m. and then I'm gonna have to review them. I might review them. So maybe we could talk about it Monday or maybe on Wednesday of next week at the very latest. That's a good question. Okay. I am going to, I think, pretty much call this the weekend here. Let's go over to, I've got a couple more slides just on Kepler's laws, which we might skip, or I might talk about those on Monday. Monday, what I'm going to do is actually start up an impulse and linear momentum. And here's a locomotive coming at you with a bunch of linear momentum. So I'd like you to read about conservation of mass and conservation of momentum. And something to think about is if I've got, where's my tennis ball? It's rolled away. But if I've got like a basketball and I throw it up and it comes back down again, is momentum conserved while the thing's going up and coming back down? And so during free fall is the momentum conserved. So I am going to turn off this one for the next 30 minutes. I'm going to be in the Physics 131 Help Center, just right over. I'm just going to walk over to the other computer. It's open right now. So if you go over there, there's your Zoom meeting ID, there's your passcode. There's also a link that you can find on the Quirkus website under the, I guess it's called TA Help Center or something. That's where I'm going to be for the next half hour, and then I'll pass the baton over to the TA when they arrive there. So I'm actually going to log off of this one. That means I get rid of this ribbon, which is good too. So thank you very much, everybody, and have a fantastic weekend, and I'll see you on Monday.